Especially in recent years, the miniation, the intelligentization, and multifunction, and other development trends of space missions have put forward high requirements on the performance and reliabilities of space components, especially the wide applications of COTS, in commercial space field and the rapid development of new and complex semiconductor devices are challenging the traditional components quality assurance technologies. So therefore, the quality assurance of EEE components has attracted highly attention of the world space industry. Today, the presentation is introduction to the system and the current development of China space components, given by Mr. Zhang Lei. Ms. Zhang is a senior engineer from China Aerospace Component Engineering Center of China Academy of Space Technology, CAST. This center is a technical institution that focused on quality assurance of space EEE components. They have carried out components engineering of all CAST spacecraft for more than 30 years and more than 200 spacecraft, and accumulate rich experience in this field. Ms. Zhang Lei will introduce the quality assurance system for space components in CAST, share the research development of COS components, quality assurance, and flight validation technologies, and propose some suggestions on the international cooperation. Now let's welcome Mr. Zhang on stage. Please.
Okay. Good morning, dear colleague. It's my honor to show the presentation on behalf of CASIC. Today, my presentation is about component topic. Of course, compared to the spacecraft, components topic is really a basic things, but it is also same to spacecraft when we talk about performance, quality, schedule, and cost requirements. As a result, we need to set up a EEE quality assurance system, just like a spacecraft engineering system. And during the past 30 years, CAST has done this, and this system has also been well practiced during the whole spacecraft design cycle. Today, we are facing many new technique development and challenges, such as commercial space and new complex devices. As a result, CAST quality assurance technology system still need to improve and perfected. Today, my presentation includes the three parts. In the first part, before technical notes, technical contents, I like to take several minutes to generally introduce CASIC. CASIC is founded in 1984. We are affiliated with CAST, and during the past 30 years, CASIC has been the pioneer organization specializing in components quality assurance for space application. CASIC is located in Beijing, and we have two sub-centers in Xi'an and Yantai City. Now we have over 25,000 square meters office, and in which is about 7,000 square meter clean laboratory. And we have over 1,000 size equipments. Now our employees number is over 240, and of which 160 are technical researchers. CASIC focused on component engineering. This is our capability that includes qualification, process control, reliability analysis, radiation evaluation, and application validation, and so on. CASIC plays as a role just like a bridge between manufacturers and end user. But it should be noted that we are not just a third party. Actually, we are a second party. That means we are fully responsible for the quality, the components quality in the whole spacecraft system. Through the quality assurance, CASIC will offer high reliability components, and we will issue the certification for each component before used in the spacecraft. Now our job has covered all area of space project forecast, and also some other space project in China, such as telecommunication, remote sensing, navigation, science exploration, and manned space flight. This is our certification. Now CASIC has been certified by China National Space Administration as a Space Components Inspection and Evaluation Laboratory. Next is our space components quality assurance system. We separate the whole system into 3 phases, from the beginning components research to the final components delivery. In phase 1 is components research and development. We will confirm the R&D plan and requirements for each component, and we will do IP evaluation and supervision in R&D process, and examination for manufacture and product line. In phase 2, maybe the work is mainly test and inspection. We will, based on the specification for procurement, we do the limit evaluation test and qualification test, such as radiation test, and to do application validation test. In the delivery phase, we will do procurement management and some general quality assurance items, and also we deliver data package, and after delivery, some storage and application guide work will be done. Next, I will choose several steps to do detailed explanation. In phase 1, the first is IP evaluation. Today, more and more complex components are widely used. We found we will not just wait for the final products and to do just some test. Actually, we need to do the evaluation for the correctness in the design procedure and along with the manufacturer. The detailed work in this step includes security rules check, prototype validation, simulation, and functional verification, and so on. Next is process identification documents establishment work. We use the PID document as a tool to control the component's technical state. And we think we will not just rely on the manufacturer's self-control. We need to combine to issue such documents to control the state. In these documents, such contents is included, such as introduction to the components, organization, and purchase processing, also material list, and product and testing requirements, non-conformance control requirements, and so on. In phase 2, the first work is to establish procurement specification. Each component for our spacecraft, we will issue such document Include is general requirements and detailed requirements for such as forbidden technology, process control requirements, material list, and also some test method, test criteria, and QC acceptance inspection requirements. So usually we use this specification as just like a technical agreement to the contract, procurement contract. And in phase 2, for the qualification test, we also do the very important work. It's a radiation test. We do TID test and a single event effect test, and also displacement damage test, according to the different process of the semiconductor devices. Except electronic test, we also do some physical test, some physical reliability analysis work. We call it AAA analysis. Among these, very important is construction analysis when we choose new components, especially for cost. Before we choose this component, we will do construction analysis to see if some forbidden material, forbidden process, and forbidden construction has been used in these components. And the final work in phase 2 is application validation. Actually, it is a new work and a new technology, but in recent years, this work has attracted more and more attention, because we found if we just do component level test, it will not totally reflect the reliability for the component. So we need to do application validation for the newly developed electronic components. And sometimes we need to speed up the proceeding for application of such new components. This work is necessary to be performed on new components before their usage. And such test is not just a component level test. We will set up some onboard test and even system level test to get the guidelines based on these experiments and evaluation result, and to guide the application for such newly designed components. In phase 3, that is the delivery phase, we will implement such work. Includes supervision, the material control check, design conformance check, and acceptance check, and some problem feedback and correction, and also do some additional screening, failure analysis and correction and verification, and also some periodic evaluation for the manufacturers. And here we also showed some requirements after delivery. Actually, previously, the quantities for the components in one spacecraft is small. So this problem is not so large. But recent years, more and more large satellite constellation projects are running, and the components demanding for the quantities has growing larger and larger. So that means we need to buy more components, one batch, and we need storage more components. So we need to pay attention to the storage environments and be careful for the distribution and packaging for the components, and also be careful of ESD protection. Next, I will introduce some new work and some cooperation direction. In this part we talk about two topics. One is cost quality assurance, and another is components flight validation. It is widely known CORS has some advantage in the space application, such as it is pre-verified and has a lower cost and high performance and rapid application. Of course, it is also widely known is the problem is reliability for the CORS components. Based on many years' practice, Classic has set up a quality assurance flow for CORS components, from the inner selection proposal to the evaluation for the risk for the components used before used in spacecrafts, and also some 100% screening, and includes many basic tests, and also some radiation evaluation tests. In the following page, I will show some detailed ideas in the research for CORS application study. The first is commercial large-scale semiconductor devices. For these chips, these usually are not radiation hardened, and normally for power supply monitoring during SEL test, it is hard to control. And Classic's recent research focuses on observing and controlling the SEL effect through monitoring the chip temperature, not the voltage, and not the current. The further research is carrying out to build up the relationship between temperature and current, and the connection between temperature and potential damage to the chip is going to be found out. The second is evaluation method for board-level radiation hardened design using pulse laser. We choose some commercial memory to test with pulse laser to evaluate the effectiveness of board-level SU hardened design. And the energy level of laser can be transferred to the equivalent LET value. Above is active components. Actually, for passive components, CORS components, we also have some research for the application reliability, such as a BME capacitor. And for such capacitor, it is a problem to evaluate its applicability in space projects. And in this research, we use the EBSD technology to observe the ceramic crystal structures, and also we use the low-stress polish technology to obtain the samples. And this analysis by EBSD technology can offer the precise scale data. In such a way, the possibility of crystal boundary damage caused by white or thermal corrosion could be pre-evaluated. So we can call that we have found a fast way to evaluate the applicability for such a capacitor. Commercial aerospace market is expanding in China, especially for the rapid developing of the low-orbit satellite. In this year, CAST has announced our Hongyan low-orbit communication satellite constellation project. And in this such project, CORS have been paid more and more attention. So we call for international cooperation in research and engineering for such for CORS space application, in such as CORS application risk evaluation technology, research on failure modes and mechanism of CORS, and technique of test and inspection for CORS. The second topic is components flight validation. About presentation, I have mentioned ground application validation technology. And we also found for advanced components, maybe only ground validation test is not enough. So we need to set up the flight validation for such components based on ground test result. We will choose such components and to analyze the risk for such components used in spacecrafts. And then we design the experiment unit according to the characteristics of such components, and put such components on the PCB to work and gather some information, some data, such as voltage, current. And in order to get high efficiency, we integrate such experiment unit to a whole experiment device. And such device will be loaded into some platform, such as in satellite and some others, and to launch and get the data. After we reserved the data, we will do the component space application capability evaluation, and we will evaluate application design technology, and also we will have more on-orbit reliability data for such new advanced components. And we can, by this way, we can enhance the technology readiness level for such advanced components. This is an example we do. Maybe last year, we use a platform for Chinese Tianzhou #1 cargo ship. And we choose a memory, DC-DC converter, and some processor to do such orbit flight validation. And also we design the device and loaded it in the platform. And we gather such data, such as current for processor and voltage for memory. We have finished such application validation along with the cargo ship last year. And in the next several years, CASIC has got several projects supported in the flight validation area. As a result, we call for international cooperation in this area, and we can use our satellite and even Chinese space station platform to do this work, and to research on exploration for new mechanisms and behaviors of such advanced components, and verification for the effectivity of ground environment, simulation theory and methodology for space, and verification for the TRL of EEE components, and also some new conceptual EEE technique, which may have an enormous evaluation for spacecrafts. So, welcome cooperation on engineering technology of space components. Thank you. That's all. Thank you.